All right. Welcome, everybody. This is Flat Earth Civil Discourse, episode 13 with JC Emond. I do apologize for all the delays, but I do want to have a big shout out to Sean Hufford, who was able to come to the rescue and teach me exactly how to launch the Hangout. So JC, say hello.
Hello, how you guys doing?
So I'm not sure how many people are going to be here because when I canceled I was on a webcam stream. When I canceled that, I think it may have closed the chat. Certainly closed it on my end. So we may have not a very big audience at first. So maybe we'll just do a little bit of small talk, and then we'll get into the introductions in a few minutes.
Yes.
So JC, you said you had some forest fires near you last week?
Forest fires. We had the lightning strike that struck all around town, and a few fires sparked up, and but it rained right after that, so the helicopter was right on it, and we got lucky this time. But last month we had up to 35 degrees in May, which is very rare. Usually the temperature is around 20 degrees Celsius at this time of year, and it was I looked like I just came back from Bermuda or wherever, and so that's what's going on. And as you can see, the sun is still shining real bright outside.
Yeah.
And it's still daylight, and then the sun will be like this till 11 o'clock tonight. And the moon is just trailing right behind it today, so we get to see the moon. The sun just passed the moon this time.
So that sounds fairly exciting. So are the fires out now? I was looking up on the web, trying to see what was going on. It was something like 190 hectares or something.
Yeah, there's another fire south of us that's still burning wild, and there's another fire north of us south of us it's about 600 kilometers. There's another one south of us that's about 200 kilometers that just took off, and there's one north of us that's 350 kilometers that just went wild also. But the forest, even though it rained for the last 2 days, the forest is extremely dry.
Yeah.
And it's a matter of time before the next, because it's cloudy and that hot temperature. I still believe it's the jet stream that's causing that. These guys are, you wake up in the morning and the sky is absolutely blue, and then by 6 o'clock, 7 o'clock, there goes a jet plane going by, and then it leaves the trail. It starts very narrow, and then by an hour, it's about a quarter of a mile wide, and it's as long as you can see. Then another hour goes by, another plane just goes past it, and then he does the same thing, and pretty soon the two jet streams join, and now the band is a mile wide, and then another hour later, another plane will go by, and then pretty soon, by the afternoon, which was a beautiful blue day, the sky is completely covered with jet chemtrails. It's unbelievable. And I believe they're doing this, personally, I believe they're doing this, is that they're trying to collect their moistures from the air. And then once the clouds or the jet stream travels toward the United States, it's loaded up with water and liquid, and then it's good for the bread basket where they grow all the food. So I think that's their plan. But I believe that it backfired on them because they're having tornadoes and they're having unbelievable weathers all over the world. I think it's because of the jet stream or the chemtrails.
Well, that's an interesting theory. I believe in contrails, not chemtrails, but there's a lot of interesting.
I'll have to take a picture of it or put a camera all day, and then you can watch it. Because when the regular plane flies by, yeah, you can still see the trail, the steam, but it disappears and it dissipates. But the chemtrails don't. They just keep widen and widen and widen till the whole the whole sky is covered. Now I've got a question. Excuse me.
Sure.
I don't see where the people are writing their comments.
Okay. So if you open up another window, so what you're interacting with now is a Google Hangouts window. Thanks again to Sean Hufford. If you open up a YouTube window, sometimes people call that a watch page. So go to YouTube, go to my channel, and you'll see a little icon. It'll say, yeah, that streaming or live now. And the important thing is, if you go there, you want to immediately click the mute button, because what you're going to do is you're going to hear this delay and this echo. You're going to actually hear our conversation, but it's going to be delayed a second. So then, but you'll be able to see the chat. Okay. Then what just to save on bandwidth, what you can do is the little 3 dots up in the corner above the chat, you could say pop out chat. So you can have the chat be in a little window, and then you can close the watch page. The watch page is kind of nice just to sort of see that, you are streaming what you think you're streaming. Like, oh, am I screen sharing? And then you can actually see on the watch page whether it's actually going out or not. So, but yeah.
Okay, I'm following you. So I just opened the thing. Okay, so what did well, now I've got a commercial on. I better just keep with the Hangout. A commercial
just put it on mute,
Okay. And okay, so I'll do it again then. And the mute button, all done. So there's the mute button. Okay, now I've got it on mute.
Yeah, and then but you should see the chat, right? So what I would do is click the 3 dots in the upper right hand corner of the chat, and then pop out, select pop out chat.
Pop out chat. Okay, there you go.
So chat's in a new window. Then you can close the YouTube window, so you could save on bandwidth.
Okay, I see. I get it now. I've never done that before. Wonderful. Okay, now are you again? The only thing I see is a globe here.
Yeah, I'm in my creepy basement, and so my my webcam, I've turned off my webcam because it's like a horror show down here. Like, and also there's incriminating evidence. I really don't want that to get out. So. Okay, so let's jump into to the shape of the Earth. So my hope is that at the end of this conversation, we will have truly decided what the true shape of the Earth is. But now, seriously, tell you were talking in the chat of one of the Hangouts. I forget which one it was. The first one I tried to start. You were talking in the chat with a couple participants about how you got into flat Earth. So you want to just tell us for the record, because this is going to be saved on video. How did you get into flat Earth? Because you expressed in your email to me that you were a space and science guy growing up. So yeah, so tell us your story a little bit.
Well, my story is when I was a kid. I was raised by nuns, and then we were all glued to the TV when the Apollo mission went up to space. I forget which Apollo it was. I think in 1969 or whatever the first. And we're all standing there and watching these fantastic things. And then when I was a kid, I wanted to be 2 things: one, an explorer, or the other one was an astronaut, because I thought space was the most fantastic thing. And then the nuns for Christmas bought me a spaceship that was operated on battery that stood up on A, and then all the lights, and I thought, oh, that was the most. And we clipped all the clippings of the astronauts, and we had a big scrapbook, and I was absolutely fascinated with that. Then
sorry about that.
No problem. Then the Star Trek, Lost in Space, and all these shows were on, and then I was again. I said for sure, by the time I'm 30 years old, we're going to be out there. The science is right here. It won't take very long. We're now to the moon, and we'll build more rockets, and we'll be out into space anytime now.
Yeah.
And then, to my surprise, 50 years later, nothing happened. Nothing. I'm shocked to the point where it's nearly to disbelief. A few years back, a friend of mine in the Philippines said, JC, you see that island over there? Well, yes. He says, do you know that we're not supposed to see that island, which is about 120 kilometers away? And I said to myself, well, no, you got to see the island. Look, we can see other places all over the place. And I get onto my boat, and I got a 30-foot boat, and I go out there, and I see islands as far as if the sun is on your back, you can see islands as far as maybe close to 200 kilometers. And I figured that the Earth is big. I never understood that the curvature was not that far apart. Like I thought, no, the curvature doesn't start till 100 miles or 200 miles. 300 miles. I never expected that it was just a few miles away. Then he says, well, look at this. Then I argued him. I argued black and blue with this guy. You're crazy. There's space station. There's pictures of Jupiter, so on and so forth. I bought telescopes for my kids and I did all this stuff. But the only thing we could see was just dots in the sky and then glittering lights. And I wanted to buy an expensive one, a $35,000 telescope, but I was not allowed to buy it from the United States because they didn't have a contract to sell it to Canada. But that's where that ends. So he says, take a look at the sun. Take a look at the sun. You think it's going down, but it's not. It's making a curve. And I never paid attention before. And now when we're sitting on the beach, and you would think that in the equator, when the sun goes down, it goes down to the west. But now that we're watching the sun, it's actually making a curve and it's turning towards the north. And the daylight starts to go towards the north, and the night lights start coming from the south towards the center of the. I said, my goodness, how come I never paid attention to that before? Then I got into the research. Okay, well now what's curvature? So I went like everybody else, and I went after Eric Dubé and everybody else that were start talking. I went through all the channels because I needed to see there's something wrong there. Either I'm crazy, they're crazy, someone is crazy, or somebody's lying to us. Well, to my conclusion, after I've discovered the curvature and then all those things that they're talking about, to me, first I said, well, no, the boats are going down over the horizon. And then now you can see with all kinds of websites that you can zoom on those boats as far as you can imagine, as far as the lens can allow you. That's JT Tolan there. He gets up in the sky with the plane with the infrared camera, and you can see as far as you can imagine. People are saying, oh yeah, well, we can debunk this guy because he's 35,000 feet up in the air and you can see further, but that's not so. The curvature still bends down forward, and there's no way. He's traveling through, I believe, through Nevada or somewhere down, and you can see Hudson Bay. Like, I mean, that's unbelievable when you look at that and it's, well, that there's a problem here somewhere. But the shape of the Earth, I don't believe it's flat.
Okay.
Well, now my point is this: is that you got the Andes, you've got the Rocky Mountains, you've got all of these mountains that they go up to 6,000, 7,000 feet, 10,000 feet, 39,000 feet. You've got all of these mountains. So the Earth is actually a big bump, like bumps here and bumps there and bumps there, and all the water flows down to the level of the ocean. That's what I understand. The Liard River here in the Yukon travels 800 kilometers. To me, at no point in time that water goes uphill. And then now, based on curvature is not only forward, but curvature is all around you. It's to your left, to your right, to your back, to your every direction of the compass. Curvature appears at any position. So the Liard River, now I'm going to talk about the Liard River, it takes off from the north and it flows down south for about 200 kilometers. Then it shoots to the east for about 400 kilometers. Then it takes off to the Arctic for another 500 kilometers. You're telling me that the water goes over the curve, down on the other side, to the left?
Well, what you have to understand about curvature and the water is we feel the people who know the Earth as a globe know that sea level is equidistant, more or less equidistant from the center of the Earth. I mean, it's not exactly, but basically when things are going over the curve, they're not, it's not like water pouring over a bowl in your sink where it's literally falling off the edge of the bowl. When we say go over the curve, it's level. It's like sea level. So it's not flowing over the curve like it's going to pick up steam. Does that make sense?
Yes and no.
So you can have like 100-mile canal, like they talk about the Suez Canal.
Correct.
The Suez Canal that doesn't violate anything. It's at sea level or at canal level, whatever canal level is.
Correct.
And it goes over the curve, but like the curve, the whole curve is sea level. There's no water flowing north or south.
Well,
So
okay, we have these giant lakes that are 70, 80, 90 kilometers long. And I can assure you, when the ice form on the lake, I don't see no curves on the lake.
Right. It's not perceptible. That is correct. It is not
And
perceptible to the human eye.
there's no bend on the ice. Now, if there was a curve and it freeze, it would freeze as a curve.
Oh
And
yeah,
it's
but if the curve is not perceptible, it doesn't matter if it's liquid water or frozen ice. If it is not perceptible to the human eye, it's not perceptible to the human eye. You're not, it's going to look flat whether it's frozen or whether it's water. Does that make sense?
well, and it does make sense. But if you put a pin on an orange, or a pin on a softball, or a pin on a beach ball, a giant beach ball, and you put a pin on it, and then you draw the Liard River on the ball, and then the pin is over here. The water has to go up no matter what,
No.
over the ball, down to the other side, no matter what. However you see it,
Yeah.
it has to go follow. If you follow the line,
Sure.
the water has to go up.
So JC, a very, very common misconception is just that you have this ball and then you trace a river on the ball, but you're holding the ball in your hands in the presence of Earth's gravity. So it's like you've got this model ball, but you physically are on Earth, and gravity pulls things straight down. I mean, you pick up your keys and you drop them; it drops straight down.
Now we're jumping subject.
Well, no. But what I'm trying to say is the beach ball that you're holding in your hand, like if you were to pour water on it, the water would go pouring off on all sides.
Well,
right?
that I understand. That's
Right?
guaranteed.
So drawing a line, the line of a river on a beach ball, you see, oh, it's going over the curve and the water would just flow over. But that's because you're in the presence of the Earth's. I mean, if you don't like gravity, you can call it downward force. I mean, like, you drop your keys, they fall to the ground. You pour water, it falls to the ground. So you have this beach ball in your hand, but it's in the presence of the downward force. Do you see what I'm saying? So that's why the line of the river doesn't make sense.
It's an imaginary concept.
Yeah, well, the thing you have to understand is
concept. I believe in the assumption that buoyancy and either it floats, or density or buoyancy, either it floats or it sinks. And then once you start comparing the two, all of a sudden gravity disappears.
Okay, so fine. So have gravity disappear, but you have to understand that if the Earth is a globe, that gravity points towards the center of the sphere. So if you're holding this beach ball in your hand, gravity is pointing towards the center of the beach ball. So if you draw a river on the surface of this beach ball, every point on that line is the same distance from the center of the beach ball. That's so it's level. It's at sea level.
Wow. This is what you're talking about cannot be measured and cannot be seen.
Oh, it can be measured. It can't be seen easily. It's very hard to see curvature, but it can be measured.
Well, it's not that hard if the distance on Google says it's only a mile per whatever times squares. So either that distance exists or that distance doesn't exist.
Well, okay, but then there's
a straightforward question. This is a straightforward answer.
Sure.
If the distance on Google Earth, which is, I don't want to put it up right now, it shows you that for every mile it drops times 2, times 2, times 2. It doesn't take very long before the water should be dropping also.
No. The again, you're mistaking the curve for like.
Well, hold on. Now we're talking the distance and the vision of the distance.
Right. So, but the water's not going to flow over the curve. The water can be level on a curve. Okay, so the water could be the same distance from the center of the Earth. So when you talk about the 8 inches per mile squared formula, oftentimes that is misused. So that the 8 inches per mile squared formula is a good estimate of Earth curvature, but it assumes that the eye line is level with like sea level. And most people don't have their eyes at sea level. They're standing up on the beach, or they're even in a building, or they're on a cliff, or they're flying in a plane. So you could see much further, quote unquote, than you should, according to 8 inches per mile squared. So are you familiar with the online?
Yes, but the much further, we're talking about 20, 100 times further.
No, it's not. No, it's not 20 or 100 times further. It's a half a degree further at most, at least according to everything I've explored. So here's a question for you. Are you familiar with the online curvature calculators? There's one at Metabunk. There's one at GitHub.
Yes, I'm familiar with the one on Google.
Well, no. I don't. Well, okay. I don't think there's.
I'm familiar. Yeah. Well, I put the island in question that's 120 kilometers away, and it's telling me that it's supposed to be 700 feet below the curvature.
Oh, okay. Okay. So I think you're using 8 inches per mile squared.
Correct.
Okay. So that is a formula for Earth curvature. It's not a formula for what you should see. And I think that's the one of the biggest problems that people have is that you need to take into account viewer height. So if you were using that calculator and it didn't ask you how high you were above the water,
Yeah,
then
it
it's
did
going
ask
to,
me that.
I'm sorry.
It did ask me that, and
Oh,
I'm at the beach.
oh,
I'm at
okay.
beach level.
All right. So we'll
About
say
5 feet tall.
6 feet above the water. Okay.
Yes, correct. Yeah.
But you should see further than just 8 inches per mile squared will give you. The second thing is there's atmospheric refraction, and it's not a whole lot. In my experience, it's and I've explored all these little photos like
Yeah.
Mount Canigou and all these like long distance photos. I've explored every single one, and I've done the math, and it's a half a degree of refraction at most.
Okay.
Oftentimes it's less than that.
Okay. So let's jump to the stars then. We seem to have a debate on water going uphill. It's okay with the system because you believe that gravity holds it in position, even though there's a drop on each side of it.
No, there's no drop. There's no drop. They're all the center. Take the beach ball example. There's no drop if you're thinking about how far each point on the beach ball is from the center of the beach ball. If that distance is constant, there's no drop. Okay? Because if the Earth were a globe, all right, and we have gravity, then every point on the surface of that beach ball is the same distance from the center of the beach ball, which means
Well,
there's no.
I think you're wrong there.
Okay.
A reason why you're wrong. When you travel to British Columbia, you come across what they call the Great Divide. And the Great Divide, once you get to the top of it, the water goes to the Arctic, the other water goes to the Pacific, and the other water goes to the Atlantic.
Sure.
So now your position of the center of the Earth no longer matches the theory that you're talking about.
Oh, okay. Okay. So let's take this beach ball and then let's take a little lump of clay and just start and let's start smoothing some clay on the surface of it to make the surface imperfect. But the point that I'm trying to make is that if you consider the beach ball to be sea level, yeah, you could have mountains that are higher than sea level, but sea level on the globe is, and I'm just going to use round, approximately the same distance from the center of the Earth. It's not exactly, but for argument's purposes, that's why when you go over the curve, you're not going downhill. You're still the same distance from the center of the Earth. So sea level is level. The water's not flowing north; it's not flowing south. You're not flowing over a curve like you're going over a waterfall. Does that make sense?
Yeah, it makes sense. What you're saying makes sense, but
Okay.
it has to be proven.
Oh, sure, and that's where careful measurements come in.
Yes, it has to be
So,
proven.
are you familiar with the theodolite?
Go ahead.
Are you familiar with the theodolite?
No, I'm not sure what a theodolite is.
Okay, so a theodolite is a precision instrument used by the world's surveyors, and if you want some bona fides, if you were going to build a $1 billion nuclear reactor or some airport in Dubai, and it's you need to have things be accurate. What do the surveyors on site use? They use theodolites. Okay. And all a theodolite is it very, very precisely measures angles left, right, and up and down.
You mean the stick with the bowl on top of it?
Right. So you'll have another guy and he'll have a stick, I mean, that's the old fashioned way they do it. Now
the one on the hill that they're all referred to, and that's the one. Yeah, I watched those guys in the construction also, and I watched those guys doing that all the time.
Yes.
Yeah.
Yes. So yeah, and there's various, qualities of theodolites. There's, robotic total station ones where, the thing sort of does all the work. And then there's manual ones where you're, turning the dials and sighting in. But basically you're measuring angles very, very precisely. And one of the most important things on a theodolite is level. So there's a surveyor, Jesse Kozlowski, and I think last year, maybe 2 years ago, he went out on a lake, and or it wasn't even a lake; it was a pond. And so he shot a level line. So he set up his theodolite, and it was literally 1 mile wide. And you looked at the water on this pond, and it was as flat as could be. So he went to the other side of the pond, and he set up a stake, measuring stick, and he measured exactly the same height off the water as the theodolite was. And then he, sighted in. And what he found was that the marker was 8 inches below where it should have been. It was 8 inches below the level line. In other words, he's looking across the lake or this pond, which is flat as can be, but yet the far side of the pond is 8 inches lower than it should have been. In other words, it was curved water. Like the water that looked flat was actually curving down, and a mile away, it was literally curving down 8 inches. It was pretty dramatic.
It is quite dramatic. Now, my next issue with I have is with the North Pole, the North Star. We are supposed to tip 23.5 degrees in summertime, and then tip back in wintertime 23.5 degrees. Well, the North Star doesn't change at all. It doesn't drop down to 23.5 degrees. It doesn't move up towards the center. So we have an issue with the tilt of this planet. It's either tilting or it doesn't.
So the Earth is not tilted with respect to the stars. So the Earth, it's turning on its axis, which makes it spin like a top. I mean, I don't like the word spin. It's turning extremely slowly, but it has a huge amount of mass, which makes it very stable. So the axis of rotation of the Earth points in the same direction in the stars all the time, year in, year out, season in, season out. So it does point very roughly towards Polaris. The north pole of the Earth points, I think it's like a degree off. It's very, very close to Polaris. It's not exactly at Polaris. But because the Earth is turning on its axis and it's so heavy, the Earth is not changing its orientation with respect to the stars. Wow. So what's this tilt we're talking about is it's tilted in respect to its orbit around the sun. So the sun will appear 23.5 degrees higher or lower than it is, say, at the equinox. But Polaris will be within a degree of the North Celestial Pole. Does that make sense?
Not really, because it's either tilt or it doesn't tilt.
It's not. So then I'm going to say it's not tilted. The Earth is not tilted with respect to the stars.
So if the sun, the stars, if the sun, in order for the planet to warm up in the summertime, it has to be tipped forward.
Yes.
So that no matter what, it has to tip forward.
To the sun, yes. But we're not talking about the sun. We're talking about the rest of the stars in the celestial sphere. All the constellations. Everything else. But yes, technically the sun is a star. But
you cannot just tilt to the sun. That's like all the celestial mass. They don't move. They're sitting over there. There's stars sitting over here. So you cannot say it's only tilted to the sun when it doesn't tilt to the stars.
So let me give you another.
Why can you see the Great Dipper all the way down to the equator when it should be buried on the other side?
Well, the Great Dipper is a circumpolar equation, or a circumpolar constellation for most latitudes. Now the thing is, if you're standing on the equator, you should only see the Big Dipper half of the year, because the Big Dipper will be up above the horizon in daylight half the year, and then it'll be above the horizon in nighttime the other half of the year, roughly. But getting back to the stars, because I really want, because I think you have a misconception, and I would love to clear up this misconception. The Earth is not tilted with respect to the stars, full stop. So there is something called the celestial equator. So there you can actually identify the stars, like the Orion's belt. I think the left hip of Orion is right on the celestial equator. And then, of course, Polaris is our north celestial pole, or at least it's a degree away. So the Earth is absolutely not tilted with respect to the stars, season in, season out. Okay. Now imagine that the Earth now the Earth is not stationary, but imagine that you were just to follow the Earth with a camera, and so that the sun is actually doing an orbit around, right? Um, the Earth is orbiting the sun. But just imagine you're following the Earth with a camera, and as you go through the seasons, the sun is orbiting the Earth just from your camera's perspective. Does that make sense? In other words, you've got like a little camera. It's following the Earth around a 12-month circuit. And what would you see in 12 months? You'd see the sun orbit the Earth in 12 months from perspective of this camera. Does that kind of make sense?
Well, that's one way to look at it.
Yeah. And we're just doing a thought experiment here. Okay.
One way to look at it.
But let me finish my thought. Because, let's say the North Pole of the Earth is like pointing straight up at Polaris, right? Well, the sun is not flying above the equator. The sun would be traveling this path that's tilted 23 degrees. So when I said the Earth is not tilted with respect to the stars, that's true. But the sun, the sun is going to be taking this weird tilted orbit around the Earth, and that's called the plane of the ecliptic, and that's tilted 23 degrees. Okay.
Well, I don't agree to what I agree to what the words you're saying are fantastic.
Sure.
But the concept of when they show you in all the books, and they show you drive a stick through the Earth, and then they spin it forward and they spin the stick backward, and then that's what they teach us. Then this is what's stuck in my mind. This is what's stuck in just about everybody else's mind, is that the stick that's from the North Pole to the South Pole is sticking out of the ground, and then that stick moves this way, and
okay.
stick to the left and to the right.
Okay, so here's, and I wish I could have a visual for you, but I don't have one offhand. If you keep the sun to, like, for example, to your left, like if you have a little diagram and you have a diagram of the Earth where the North Pole is tilted towards the sun, and you have the sun on the left side of your picture, then you can call that summer, for the Northern Hemisphere. Well, if you want to illustrate winter, you're going to take that stick and you're going to aim it away from the sun. In other words, the sun is still on the left side of your drawing. The stick is now pointing away from the sun. It's now the Northern Hemisphere's winter. And that's kind of where people get the idea of the stick is flip-flopping back and forth, back and forth. But in reality, the sun doesn't stay on the left. If from summer to winter, the sun is on the other side of the Earth. So the stick is still pointing diagonally, say, up to the left, but now the sun's on the other side of the drawing. In which case the sun, the tilt of the Earth's axis is tilted away from the sun. Same orientation. The tilt of the Earth has not changed. It's just we're now orbiting the sun. So we're on one side of the sun, we're on the other side of the sun. That's how we get our seasons. But our tilt has not changed. It's still 23.5 degrees, but that orientation is always pointing towards Polaris.
All right. So we have all these beautiful explanations, which is they sound sound. I cannot disagree with you. They sound perfectly, because there's an old saying: there's more than one way to skin a cat.
Sure.
Now let's go look at the last one. My main concern. We have Hubble telescope, this beautiful thing that's sitting up there. We spend millions of dollars on it. The Canada Arm picked it up and twisted around left and right and whatever.
Canada.
At what point and when are they ever going to point this thing facing the Earth and show us Australia building sideways, in Germany the building straight to the left, and upside down in Australia, and upside down in Alaska, straight up in the air? At what point are they going to be able to give us a focused picture of this beautiful globe that we've been sitting on, that we've never seen a straight picture of it yet? At what point are we going to get this picture to validate and to stop this whole argument for once and for all?
Well, so there's a couple issues with this. One is that there have been tens of thousands of photos of the Earth from space, but all of these photos are rejected by flat Earth folks. So if we were to say, oh, we're going to turn the Hubble Space Telescope around, which, the optics are not designed to photograph something as close as the Earth. The optics are designed to focus, on stars. But, you may say that's a dodge. But we got many, many satellites, and also rocket missions to space and the ISS. And they've all photographed the Earth from space 1,000 times over. But every single one of these photographs is rejected. So if we were to turn the Hubble Space Telescope around, say, okay, Mr. Doubter, right, we're going to photograph the Earth from the Hubble Space Telescope. There's no reason that that photograph won't be rejected as well.
Well, to be rejected, to say, well, it's to create an assumption prior to put the evidence.
Well,
you
right,
have the
if you
evidence on the table. We send stuff to we send stuff. There's supposed to be rovers on Jupiter, and like rovers on Mars, and then rovers and stuff on the moon, and name it, wherever they got these things flying all over the place. And then they never turned the camera and look this way and say, this is what it looks like. And now we have these fantastic pixel that you can zoom on this baby. And here we go. There's this guy in Australia with his ship going upside down, coming towards the equator. That would be a beautiful picture. And then that there would be a continuous flow so that you would have a bunch of pictures glued together where you could see, okay, well, I want to zoom on that ship and then back up and zoom forward into Brazil and back up and zoom forward to Central America, back up, zoom forward to Mexico, and then go all the way up to North America and take a look at what this planet looked like. Because so far, with all the beautiful money, the billions of dollars we're sending to NASA and all these guys, that are creating all these fantastic things, the latest one I've seen was a picture of Venus. I mean, a picture of Mars, and then they found the same picture in Turkey, and it's a match for match.
No, I think you're thinking of Greenland.
Or wherever it was.
Yeah, but that was.
Yeah.
All right. So sometimes the cart gets put before the horse. So I've seen that picture where they show, this reddish photo on one side, and they're like, this is a photo of Mars, and then the photo on the right has got this green moss on the rocks, and the sky is blue, and it's clearly exactly the same photo. Is that the one you're talking about?
Yes.
Okay. Well, that was taken from a guy's presentation on how you can take a photo of Greenland and make it look like it was on Mars. Okay. And so what they did is the flat earthers have taken that guy's presentation and they start with the Mars version and they're like, look, we got this from NASA. Well, no, they didn't get it from NASA. They got it from this guy's presentation. They just cut out the presentation part, so that's false evidence. I mean, this guy, I mean, you could look it up on the web and it's still on there. You could find the guy's presentation on how to use Photoshop to make Greenland look like Mars, but that's now used as evidence against NASA. So,
well, all your fancy explanation to me, and not because all the fancy explanation, they don't, to my point of view, not because I'm a stubborn head or whatever, is that now when I take off in an airplane and the airplane stays level, and when I do this, because I travel to the Philippines every year, I go back and forth for the last 14 years. I'm in the south, I'm in the north, I'm all over the place. I watch water flows and I watch mountains and I watch this and that. And then I haven't seen the curve to start with. And you're going to say the curve is impossible to see.
It's imperceptible.
Yeah, imperceptible. But in an airplane, you think you'd start seeing some kind of shape.
An airplane flies way too low because the globe. I mean, like you talk about an airplane, how high an airplane flies. An airplane flies so low and so slow that it would take you 48 hours just to go around the Earth on a nonstop flight. The Earth is a lot bigger than a lot of people realize. They think it's like this, this Super Mario Galaxy type planet. But getting back to your you've traveled a lot, and the thing is, you've got a great opportunity to make some very careful observations. So here's a question for you: do you ever go south of the equator in your travels?
No, because the Philippines is just to the edge of it.
Okay.
Hold on, I go to Malaysia. I think Malaysia is on the equator.
Okay. So you have a wonderful opportunity to, and you mentioned this earlier, like when you see it, when you see the sunset, you're like, all right, so it's sweeping towards the north a little bit. Well, one of the things that you should have noticed when you're on the equator or very near the equator is that the sun almost hits the horizon almost at a 90-degree angle. I mean, it is tilted a little bit, But the flat Earth model would have us believe that the sun is actually horizontal, flying in a plane horizontal to our horizontal ground, and yet you've seen with your own eyes the sun goes not straight down, but at a very slight angle, but almost directly straight down, almost 90 degrees to the horizon. Yes, tilted a little bit, but that's like a huge difference than what the flat Earth model would say, which says that the sun is actually going horizontally. Do you see what I'm saying? So you're 90 degrees off.
Now, then again, they have another valid point that when the horizon collapse, everything seems to collapse. This guy makes a dime disappear on the table as he moves the dime back and forth on the table.
Sure.
So, and it's not magic and it's not trickery. It's the horizon. It's what the horizon does. It collapses on itself.
Okay. So let's say this collapsing horizon was a true thing. Okay. Let's say I'm just going to grant you that point. Would that turn a horizontal trajectory into a vertical one? Like would that make a plane that is literally flying east to west, would it make it look like it was flying directly at the ground? Do you see what I'm saying? Even if you were collapsed the horizon,
But they seem to disappear before you get to see them. Okay. Well, let's take a look at a jet stream then. A jet stream. When I watch a plane, like I can see a plane maybe 70 mile, 80 mile, 90 mile away, and it comes across the sky, and then I can see it going the other way, another 80, 90 mile. Now he's probably 50 mile from me. I don't see a curve in the plane, and then
sure.
we're looking at a plane flying. I can see a distance of about 300 miles of this plane going from the east to the north. I mean, from the west to the east, and I can see that plane from a long way yet. And then when you look at the sky, there is no bend in the curve in the.
So
In the
I think you're overestimating how much of the plane's trajectory you can see. So whenever I've spotted a plane in the sky, like we're talking about a jetliner at cruising altitude,
Correct.
I've never been able to see it for longer than a few minutes. Okay, like before it disappears from view, either over the horizon or whatever. And so, what's a few minutes at 500 miles an hour? Well, that's maybe less than 50 miles. Okay, so if you say that you can see 500 or 300 miles of this plane's flight, that means you're watching one plane for 45 minutes at cruising altitude. Do you see what I'm saying?
Yeah, I see what you're saying. I'm just looking at a plane, and they're 40,000 feet up, and then you can see it coming, and then you see that stream, and you can see that.
But here's the one of the focuses of my channel, and I guess that's how you discovered me, and that's how we're having this conversation. Is you made a comment on my channel, and I appreciate that. But one of the focuses on my channel is on making careful observations. So the next time you see a jetliner, like and look at the horizon, like try to find one that's like just coming over the horizon or whatever, and then take out your stopwatch or just make a note of the time to the second, and then just watch that thing go. And then when you just barely can't see it anymore, or just when it drops off from your view, make note of the time again, and then just notice the difference in times, and just do the math and just pretend it's going 500 miles an hour.
Yeah.
And then you'd be able to do the math. You'd be able to say, I'm seeing so many miles of this jet's travel, assuming it's going 500 miles an hour.
Yeah, you probably see 100 kilometers.
Well, but what I'm saying, do the math, because a lot of people, they make casual observations. They make casual observations, and then they draw all sorts of interesting conclusions. And then what I say is, make a careful observation. Like the next time you're down in the Philippines, I want you to pay very close attention to the angle that the sun is making with the horizon. And I'm telling you, you should be able to predict your latitude by looking at that angle. Like if you're at 5 degrees north latitude, the sun's going to hit the horizon at about an 85-degree angle.
Then let me ask you a question.
Oh, sure.
So what is the distance on the water based on the other place that the other formula that you talked about? What is the distance before you don't see the bend? Before you don't see the horizon no more? What is the distance before the curve start on the other?
Well, I'm not quite sure if I understand your question, because Like, are you asking the distance to the horizon?
No, what is the distance to the curve on the other two websites that you mentioned?
Well, okay, so all these websites, they all use, pretty much similar formulas, and you could derive the formulas yourselves. But the curve is continuous. So, like, if you have a swimming pool, the water is curved. I mean, of course, it's not curved very much. It's curved probably like a molecule, but the water is continuously curving. It's just it doesn't curve to the human perception. So it's not like it starts curving at a certain point. Now, the distance to the horizon, that depends on your observer height. So if you're standing at the beach and you're 6 feet tall, the horizon is about 3 miles away. And if you're, up higher, then the horizon's further. So I don't think that's quite answering your question. So,
Okay, now I watched ships sailing where the ships were they were far greater. I have a boat. I take off from my island to go to another island. I got a 30-foot boat, and then it was handmade by these natives, and they cut this giant piece of wood. And then I take off with my boat 70 miles away, and I can still see the island that I'm on. That I'm talking about 70 miles. My GPS shows 70 miles.
okay.
I can still see the island that I'm on. So when does the curve start?
Well, okay. So, like I said, the curve is continuous. The curve starts, at your toes. The question, the important thing is, where is your observer height? Exactly how high above the water is it?
I'm sitting in the boat.
Right. But I mean, what kind of a boat is it? Is it a cabin cruiser? Is it a canoe? I mean,
Well, my boat is 5 feet, about 4 feet tall, but it's only sticking out 3 feet out of the water. It's got two pontoons that are 20 feet long on both sides, and it's 30 feet long, and it's made out of one plank. And they
okay.
all do it by hand, and I can take giant waves because it doesn't flip over. It's designed to cross the Pacific with it.
Okay. So you've got it's a pontoon boat. So it's very
Yeah.
stable. Okay. Yeah, those things are awesome.
And
Yeah. So if you know exactly your height above the water, I would strongly recommend you use the curve calculator over at Metabunk, because that one has it includes atmospheric refraction. And atmospheric refraction is not a huge effect. It's a fraction of a degree. All right, a fraction of a degree, but it is enough for you to see quote unquote further than you should if there were no atmosphere. All right. But then the question is, the island you're looking at, what's the height? What's the height of that island? Are there
700 or 800 feet up, it's a volcano on it. It's called,
okay.
the island is called Ibuk.
So, for example, I saw pictures, and I don't remember the names of the islands offhand, but it was one Hawaiian island looking at another Hawaiian island that has a very distinctive, extinct volcano on it. And they were saying, oh, this, you shouldn't be able to see this, blah, blah, blah. And so I remember looking at this photo and like, okay, you get this very, very distinctive volcano. It almost looks like a plateau. You've got an angle, and then there's a flat top, and then there's another angle. It looks like a classic volcano profile, right? Well, then I was like, okay, let me figure this out. And the island is like, I don't know, 50 miles away, or maybe it's 100 miles away. And then come to find out that we're only looking at like the top third of the volcano. Like the entire rest of the island was hidden behind the curvature. So this whole thing about, there's this island and here's this volcano, like we weren't even seeing, a third of it. So then I just ran the numbers, and it's like, yeah, that's exactly what we should see. So
Because there's also, now where you're talking about when you drive down the highway and you see the heat wave and you can see the reflection of the car coming at you, and there's no water, but yet you can see the car in the fake water, the mirage, right?
Yes.
And then water creates vapors also in the ocean, and then you may think that you don't see the base of the island, but it's the vapor that's creating a barrier that you don't see the base.
So refraction does have all sorts of interesting little effects, but you can take a look at photos that are taken over water. There are good photos and there are bad photos. And so oftentimes what flat earthers will focus on is the photos and the imagery where there's all sorts of refraction and mirages and reflections, and you've got a false like a reflection line where like a ship looks like a shark, because the bow is reflected, so it looks like the open mouth of a shark. And there's all sorts of footage like that. But then
Yeah.
what I would say is, okay, why don't we just take that footage and say, okay, all these mirages, it's really kind of messing things up. Why don't we go for the footage where it doesn't have all these mirage effects, where you can have a razor sharp horizon line? Because there's tons of photos with that, in mind. For you were mentioning Jay Tolan Media.
Yeah.
When he's identifying like, oh, this is, I'm in Nevada, but I'm looking at, Wisconsin or whatever, and he's pointing, all I see is clouds, right? So if you fast forward on that video a little bit, there he's taking a look at one of the Great Lakes, and then he has like, you could see it on the map, and you could see the profile of it, and that's a crystal clear shot, but like there's literally the horizon line on the lake. So in other words, you can't see the far shore of this lake. So his claim, like in other words, he debunked his own claim that you can see hundreds and hundreds of miles from his plane, because
right.
you literally have a horizon line on the lake, and it's a razor sharp horizon line.
You're right. There's an horizon line on the lake, but it could be the horizon collapsing based on the distance.
Yeah, that sounds like word salad to me.
Oh, well, yeah, but it could be both, because as far as I'm concerned, now I'm at a point where, every time a jet flies up in the sky, it always makes a curve, and then all these things, and you've got all these astronauts playing around in the space there, and playing with green screens in the back, and bouncing around fake balls, moving their hand rapidly to the left, to the right, and then trying to pass things, or they make a magic freaking puppet appear inside the spaceship to talk to the children at schools, and so on and so forth. And there's no end to this thing. There's no end to the puppetry and then the fakery that they're creating to make people believe that there's people sitting in the Vanner's belt, the belt that is supposed to be a vacuum, and you have high temperature, low temperature. We're protected we're protected in the earth. We're protected by the ozone layer, and protected by the earth atmosphere, so that we don't get burned by the sun. As soon as we get out, it's supposed to be 290 degrees. And then even the astronauts are saying, "Oh yeah, in the sun it's that hot, and in the shade of the moon it's that cold." And yet they're going over there with freaking rubber gloves on, and you can see the duct tape on their boots. Not one's got the same pair of gloves. There's all kinds of little wee things that are pointing out that looks pretty funny to me.
Yeah. So the thing that I would just recommend to you, because it sounds like you spent a whole lot of time on the ISS is fake, or where the people who make those videos, they will literally comb through 20 hours of footage, and they'll pick out like the 5 frames that look fake, or whatever. And it's like, well, what about the other 20 hours? Like, how come you're not focused on that? Like there was this one where it was a group of astronauts, and one of them did a front somersault, and then like the guy next to him kind of reached out, and his finger kind of tagged his pocket, like as the guy was turning around. You're like, look, there was a wire, there was a wire. And then, well, if you continue on with watching the same video, you see those astronauts do like side rolls, like, so if the guys, the argument was supposed to be that the guy was being held up by a harness on his hips, like 2 wires, like in the circus,
That's
you have
yeah.
like you have a belt on, and you have 1 wire on your left hip, 1 wire on your right hip, and then you could do a front somersault. Well, if you had that harness, you could not do a sideways somersault, like what they call a heartline roll. And so it's like, so they cut out the part where the guy does the heartline roll, and they only include the part where he does a somersault. And then he says, oh, well, look, that there's a wire there. So it's like the people making those videos, they are very, very selective with what they pick.
They're doing a good job.
Well, the thing is, so here's what I'd recommend, because you sound like a reasonable person. You're questioning, and you are right to question stuff. But what's the other side? What's the other side say? If you watch documentaries made by flat earthers, or made by people who say NASA is fake, watch documentaries made by the other side, like the people who are fans of the space station. like there was this walkthrough of this, not walkthrough, but a fly through of the space station. And it's like 30 minutes long. And you can clearly see that like there's no way that there would be any kind of harness possible that would be able to hold this person up. And I mean, the thing is, I could kind of go on like with all the stuff that I've seen, and it could be explained away, but like I have an eye for detail. And so you've heard about the hairspray thing, like with a woman with a lot of hair, and then they're like, oh, the hair is being held up by hairspray. Well, when someone's underwater and they've got like a big head of hair and they're underwater, notice when they turn their head, the hair does not turn until a moment later, because like the hair is, it has momentum. So if the person turns their head underwater, well, the hair's got to catch up. So I was watching some ISS footage, and there was a woman, she had this big, it looked like an afro because her hair was sticking up. But I noticed her just turn her head sharply, and her hair had a delay. In other words, hairspray doesn't do that. Like if you have your hair sticking up because of hairspray, it's like a helmet, I'm sorry. What'd you say?
No, I follow what you're saying. It makes sense for that.
But that's subtle. That's very subtle. Like the effect that I'm talking about is not an obvious effect. It's a subtle effect that indicates that her hair was not being held in place with hairspray, and that's one of the big arguments. There was another one where there was a woman wearing a necklace, and it was like a HD video, and I zoomed in, and you could actually see the individual links of the necklace were floating in relationship to each other. In other words, like there were 0G links on this necklace.
The 0G plane you're talking about.
I'm sorry?
There's 0G plane.
No, but this was in a 30-minute long fly through of the ISS, and then then the argument would be, oh, well, that's all CGI. So it's like, that's just the fallback. So I would just recommend that, as much time as you spend watching the ISS is fake, then watch an ISS documentary, and then look at the footage yourself, because you'll find that people are very, very selective with what they pick.
You've got all the answers. What about have they made it to the moon yet?
Of course. There's a prodigious.
You're telling me that the rubber tires that they have on the moon ship can withstand the temperature of 280 degrees Celsius.
Okay. Did you say rubber tires?
Or what kind of tires they had on?
They were made out of springs. I mean, just take a look at any like literally just Google, lunar buggy or lunar buggy tires, and you'll find that they were literally made of like springs covered with like a wire mesh.
Oh, I see.
There's no rubber.
What kind of cargo plane did they use to bring the stuff up there?
What? I'm sorry. Did you say cargo?
Unload the stuff, all these trucks and these vehicles and the stuff that they had out there, the lunar vehicle, for example. How did they manage to unload that? They didn't have the kind of the arm on there to drop that thing up and by itself, or did they land it there with a parachute?
So, well, if you actually do the research, you'll find that I'm pretty sure Apollo 11 did not have a lunar rover. And I'm not quite sure which the first lunar mission did have a rover, but it was folded up, and it was, I guess they called it the lunar buggy or something. It was folded up, and it was bolted to the outside of the lunar lander. So when they landed the lunar, I mean, it was designed to work. Like, for example, you sound like you're scientifically minded. If you were designing, say, an RV, and you wanted to have a motorcycle, you wanted to, you've seen that on the highway, an RV. Well, you wouldn't put the motorcycle on the roof of the RV, because then the question is, well, how do you get it down? So you build it onto a little ramp on the back of the RV with like a little, maybe it's a hydraulic lift or something. So if you were designing an RV and you wanted to be able to hold a motorcycle in the back, you would design it such that when you got to where you're going, you push a button and the ramp lowers. So the lunar buggy, first off, it folded up, because it's not really designed to look good. It folded up, and it was attached to the side of the lunar lander, so that when they landed, they just unfold it, and it's ready to go.
I guess we're imagining that, or we have documented.
You could look up the schematics. I mean, there's hundreds of thousands of like detailed engineering documents on all the lunar missions. And like, if you say, oh, how do they do XYZ, you could just look it up, because like they've digitized and published all this stuff. And the thing is, you can go to any physics teacher and say, I think this is breaking the laws of physics, and you'll find no contradiction. You'll find no, you look up, what kind of a battery they used, look up, what's the range of, how far were they able to drive, look up how fast they were able to go, and look up how they were able to get the signal back to the, like all the specs are there. And you can ask any engineer to check them out, and they're like, it's all going to check out, there's no contradiction.
We can look deep and far into space, correct? Now
Well,
we have
with the right telescope, yes.
Can we go look at that stuff that's sitting on the moon?
No, the optics don't have anywhere near precision. The thing that a lot of people don't realize is the moon is what, 2,000 miles in diameter, and a lunar rover is, what, 5 feet long. The lunar module is like 14 feet wide. I mean, there's no way you're going to take a telescope and look at something that's 14 feet wide on a, something that's so far away. I mean, it's 240,000 miles from Earth. Now, what they have seen,
I thought it was 230,000 miles.
Well, it's got a elliptical orbit. It's a pretty strong. I mean, 240,000 miles is an average. Sometimes it's more, sometimes it's less. You've heard about like the supermoon and the micromoon, and you could photograph that, yourself. You can actually see the change of size in the moon from season to season. But the point that I was trying to make is that the moon, it's a huge sphere, 2,000 miles in diameter, and it's really, really far away. And all of our lunar equipment is measured in feet, So, but what they have done is they've got I think it's called the Lunar Reconnaissance Orbiter. It's a satellite that's orbiting the moon.
What are you telling me? You're telling me that the moon is only I didn't even know that. Now you're bringing up another subject that's going to be acute to me.
Sure.
You're telling me that the moon is only 2,000 miles in diameter?
Yes.
And you're telling me that we're looking at that thing at 230,000 miles away, and we can see it that big from 2,000 miles. It's only 2,000 miles across?
Yes. Well, like, all right. So, are you familiar with angular size calculators?
2,000 miles, 250,000 miles. I'm gonna have you do the math. You're the math person. You should be able to tell me that the moon should be an inch or a quarter of an inch or a foot.
What you're going to find is it's approximately a half a degree of arc. All right, a half a degree of arc. So, for example, 2,000 miles diameter, 240,000 miles away. So let's take off the 1,000. So we'll call it 2 units in diameter, 240 units away. Well, then let's divide by 2. 1 unit diameter, 120 units away, right? So it's like, imagine taking a penny and then putting it 120 pennies away, and it's a penny. And how big is it? Well, it's about a half a degree.
I'm gonna have to check that one out.
Yeah, sure. But you'll find it checks out just fine.
So the next one that we have is the sun rays.
Crepuscular rays?
Yeah, when you look at the sun coming across, and then you can see a cloud hiding the sun, and then on both sides of the cloud you can see the rays, one side to the left, the other side to the right, and then you can calculate the distance of the sun, and it doesn't show by looking at the sun rays that is 180 million, 93 million miles away.
So you've done a fair bit of traveling, and you've spent a lot of time in hotels, I'm sure. So you look down a hotel corridor, and what do you see? The ceiling and the floor and the left wall and the right wall. What are those lines doing? Those lines are doing exactly what they do with the sun rays in a cloud. And those lines never meet. They're parallel to each other. So, those lines meet at infinity, because we're looking at a parallel of the floor is parallel to the ceiling. The left wall is parallel to the right wall. So you're looking, when you just look down a hallway, you're looking at the same effect as when you look at the sun in the sky with the sun, the crepuscular rays coming through a cloud, right? They appear to converge at one point, but they're parallel, or essentially parallel. They're within a half a degree of parallel. So
Well,
it's, that's a non-starter because you can see the same thing in a hallway.
well, that's another good question, good answer there. But to me, uh, the opening for both for both theory are open to me, and there's not one that is can justify to the point to me. There is nothing that can tell me it's round or it's flat or it's oval or whatever it is that it may be. I think I've got my limitation
Yeah,
based. There's not enough information. The information seems to be balled up, exaggerated, or numbers are thrown out into whatever numbers that they use, infinite numbers and this and distance, and then that we're traveling 180,000 miles, 180 million miles a year around the sun, and then we're spinning at this the whole system, the whole solar system is doing the same thing as we're moving through the Big Bang Theory. To me, that doesn't make any sense whatsoever. And
yeah, yeah.
it's all theories, and then they take theories and they put them into practice and they feed them to children, and children freaking have to swallow that and believe in this. And
So
then that's the same thing as medical views. The medical people, they have all their programs and they have all their teaching. And when you go to see a doctor, and they tell you, oh, well, I know I'm jumping the ship here, but when you talk to a doctor, he's got a one mindset. This is how we do things. This is how we learn. This is the book. This has been proven. It works on Joe and Bill. It works on that, but it doesn't work on all. And I think that the whole system of teaching should go back to the basic is first let's understand what we have in front of us, and then
yeah.
after that we can imagine, oh, the Big Bang is over here. This guy figured out that they can figure the thread, and yeah, they can figure the bend, and even Einstein said that the earth was flat.
No, he never said any such thing.
He said that it's a theory that the earth is round and the universe works that way. And everyone, in fact, what I read, what I understood, that everyone is stating that this is not, this needs to be proven. But somehow they threw it into the book, and it's like anything else. It's like, the victor writes the history, and then
Sure.
name it,
Yeah.
and then whoever writes down stuff, and then that's not proven to the
Okay.
book. Go ahead.
Yeah. So I get all that. And so what I'm going to do is I'm going to say, let's say you're right. Okay. I'm going to acknowledge
Oh,
the
rounder.
possibility that 100% of your points are correct. Now, where do we go from there? So let's say the whole system's corrupt. Everyone's lying. It's a big conspiracy. So in other words, throw all that out the window. So we can't trust any of that. So then what can you do? You can then go outside and make careful measurements. And that's really what my whole channel is about. So for example, if you make careful measurements of the sun, moon, and stars, then and then you compare it to the flat earth model and you compare it to the globe earth model, you may draw some conclusions. So one of the biggest things is that the moon is orbiting the North Pole parallel to the plane of the flat earth, right? That the moon is just traveling in a big circle, along with the sun. But let's focus on the moon because you don't need any special filters to see the moon. You can see the craters,
There right now. For me, I think there's a cloud right now. If there wasn't a cloud, we would be looking at the sun right now, and I can see the moon is just about, I don't know, looking in the sky. It's probably 5 feet away from no, 100 feet away from the sun. When I
Sure,
look
sure.
at the
So the point that I'm trying to make is
go ahead.
make some careful measurements. So one of the things you can do is take a look at how big the moon is at moonrise, and then take a look at the size of the moon when it's highest in the sky.
Oh, wait a
Um,
minute. Wait a minute. Now let's go back to your statement. We
sure.
have refraction. Refraction is like a magnified glass. It will
Well,
enlarge the moon.
not necessarily.
Or we don't know that. We can both say yes or no, but we don't
Well,
really know that.
okay. So let's
Take a
say
glass of water,
we're
look at something, it may look bigger on the other side. Put
okay.
some moisture in the air, and it might look bigger.
So the thing about refraction is refraction, the refraction through the atmosphere is based on the different levels of pressure. right? And so you all know, you know when you go to a high mountain, whatever, the pressure gets lower, things get colder, and you can get a little device that measures pressure, and you can actually see it. You could actually blow up a balloon, and you could see the balloon get bigger, because of the lower pressure, lower air pressure. So the layers of pressure are horizontal. So refraction is a phenomenon. Like we're looking at like something on the horizon. It's something that's going to change how high or low it appears. Refraction is not going to change whether it's left or right. Okay. So when you see the sun or the moon or anything setting on the horizon, yeah, it may get squashed vertically, right? Because of refraction. I mean, you've seen the sun look squashed when it sets, right?
Yeah.
Under certain conditions. I mean, you've seen that. You've been to the beach, but
Yeah.
it doesn't squash left to right. In fact, if you, like I said, you make careful measurements, if you take a camera and measure the horizontal width of the sun, you'll need a filter if you do it, when it's really bright. You'll find the left to right size of the sun never changes. All right. So the other thing, oh, go ahead.
There's a gentleman on YouTube that did the trajectory of the sun and the moon, and then he was documenting the size on the paper as through a hole in the box. I don't know if you've seen that, and then through a telescope and cameras, whatever. And then he was showing a graph. He was using graph paper how the moon goes through his box, and then he could calculate the size of the sun and the size of the moon, and then he could show as the moon comes up, it's a little bit smaller, and as it comes up towards the top of us, it becomes a little bit bigger, and as it goes further away from us, it gets smaller again.
Yeah, I would be interested in seeing that video. So if you could find that link and then just email it to me, I'd be very interested in seeing that, because
that's a really good one. That one was like he says, now I can and that guy did some really good calculation, some very good detail in it. And then he said, tell everybody you can do it at home. And then I was impressed. And he said, now that proves that the moon is coming at us, it's passing over us, and it's going past us, and it's changing dimension.
So the people use the word prove very, very loosely.
Yeah,
so if you actually run the numbers, I mean, you're pretty far north of me, but I'm near Philadelphia, and so the moon should roughly double in size, when it's high in the sky near Philadelphia versus moonrise and moonset, because of the distance. Like in other words, the moon is twice as far on the flat Earth model. The moon is twice as far at moonrise and moonset as it is when it's high in the sky. So I should see the moon be twice as big.
At 240,000 miles away.
No. The flat Earth model. On the flat Earth model.
Yes, but at 240,000 miles away, 4,000 miles between here and Philadelphia should make no difference size of the moon from here looking at it.
That's correct. That's in the globe Earth model.
Today, because it's been out all day. I don't know if you could see the moon all day in Philadelphia because of the fog and the pollution, but I could see the moon all day long. It's been traveling from the east. It's going just about, I don't know what angle would that be, about 45-degree angle, and it's coming. Now, the moon cycles, the shadow and the
phases of the moon.
The phase, it's not a shadow of the Earth. It's the moon.
That's right. The only people who say it's a shadow of the Earth are flat earthers who are setting up a straw man.
I don't think a flat earther said that.
No globe earther has ever said the phases of the moon are the shadow of the Earth. None. Okay. So if you've heard that phrase, you're being lied to. You're being lied to by a flat earther who's misrepresenting. Do you see what I'm saying? You gotta be careful with those citations, because there's a lot of trickery out there.
There's been the latest one I've come across with talking about the moon and the sun is that if the moon is coming around, because the moon is also going around the Earth, correct?
Yes.
And at a certain point, if the moon was round, we should be able to see the backside of it no matter what.
No.
Well, there's another place where it shows the calculation of that too. I don't know if you came across that one. It's under what's that website? I forgot the name of the website. Who they're demonstrating that you should be able to see the backside of the moon based on the way that based on the way we're rotating and
No,
based on.
they're then they misunderstand the heliocentric model. So the best way I can explain it is, if you know the game of tetherball.
Not
Do,
really.
do you do you do you play tetherball up in Canada?
I don't know what that is.
Okay,
Tetherball.
so tetherball, imagine like a pole that's like maybe 12 feet tall, or maybe it's shorter, and it's got a rope attached to the top, almost like it's a flagpole, but it's a rope attached to the top, and then there's a ball that literally has a rope coming out of one side of it. I mean, it's not a super bouncy ball, but the rope literally is coming out of the side of the ball. It's tethered. Okay. And what you're supposed to do is you're supposed to stand around in a circle, and you're supposed to swat the ball, and then the ball is going to travel around in a circle, and then somebody swats it back.
A kid. Yeah.
It's a kid's game. Yeah.
Yeah.
So
I
so
that.
if you had a tether ball,
Yeah.
like you were holding onto this rope, and you were allowing the ball to kind of fly out, like you were going to spin it around you, would you ever see the backside of the tether ball? And the answer is no. You're only going to see the tether side of the tether ball. Like there's no physical way you would ever see the backside of the tether ball, right? Because it's tethered, So if the moon is going around the Earth, and the moon is having the same face towards the Earth because of tidal locking, it happened over billions of years. That we're never going to see the other side unless we fly a spacecraft around there. So I'd be interested to see that video that sort of is proving that we should be able to see the backside, but it's kind of like proving you'd be able to see the backside of a tether ball when it's tethered. It doesn't make any sense.
I guess not.
Yeah. So we got to cut this short. The intention was that it would be like an hour-long conversation, and I'm happy to talk with you again. I think this was a very interesting conversation. I think we both kind of heard each other's points. I'm hoping. And again, that the plan was not for me to convince you or you to convince me, but for us to respectfully listen to each other's points.
Well, I follow your point. You know what? I understand just about everything you mentioned. Well, just basically everything you mentioned, because I knew that to start with. But then this other wave that came at me, and it's smashing me, and it's creating a head-on, and then I'm trying to figure out, well, what's going on now? And that's it. And then I'm at that same stage. And then till the day I understand curvature completely, then to me, then I'll have to make my decision based on that.
Yeah.
Because I really love to, personally, I really love to go to the prairies where it's extremely flat for 1,000 kilometers.
Sure.
And do a level experiment on the prairies. And at what point if you shoot a straight line with the machine that you talked about, because
theodolite.
Yeah, and then if you shoot a straight line, at what point and at what distance it starts to get up in the sky and the ground's going down. And this is what I like to do in my spare time, but go across Canada, only in the prairies, because somewhere else is pretty tough to do. You've got mountains, you've got this, you've got that, but the prairies would be an exciting place to do it with.
Yeah. If you could get a like a builder's level, it's looks like a telescope, but it's got a little leveling device in it, and like a little crosshairs. And I think they sell them for less than $100, maybe. Maybe a lot less than that, depending on the quality. But if you can get like one that has like a 24x magnification, it goes by various names. But if you look up builder's level, but that is something that is literally the size of a very, very small telescope. I mean, it's like the size of one half of a binoculars, very, very small. So you can take it with you, as you travel. And that would be really neat to look, because then you'd have a level line, So no matter where you were, you look through this thing and you'd be able to see the level, because there is a piece of human psychology that is the eye is drawn to the horizon. And flat earthers have taken that phrase and they've turned it around to the horizon rises to eye level, and it's really the other way around. The eye is drawn to the horizon. And it really doesn't matter if the horizon's up, if the horizon's down, the eye is drawn to the horizon. But if you had if you had an actual precision instrument in your hands, you'd be able to see, the horizon being below eye level. So anyway, I think we're going to cut it off here. We've got a bunch of people in the chat who have been having a great conversation. I'm sorry if the people in chat were trying to get my attention, because I wasn't really paying attention to it. But thank you very much for everybody in the chat. Thank you for JC Emond for joining me. It was a great conversation. Any last words, JC?
Well, keep up the good work. No matter what you teach, and then but don't let anybody else. My daughter. I said, this is what you see. This is what you get. If there's something else, well, then you'll have to experience for yourself. And she's 6 years old, and she believes that the Earth is flat because this is what we're looking at.
All right. So I'm going to cut off the broadcast. JC, don't hang up just yet.
Okay.
Again, thank you to everybody in the audience. Have a blessed rest of your weekend. Bye-bye.
Thank you.